And I'll give a more example for that. So that was example. The second system here is maybe more complicated here. Yn equal to summation of k. I have ak here of yn minus k. K will go directly from 1 to n minus 1 plus summation L from 0 to n minus 1 x n minus L. We are missing here Vn. Okay, so this system is every time I have to compute an output sample Yn, I look at in the past my output and the input signal, and I take some of those combinations. Okay, so that's another example of a signal. And you see this thing here, I can easily write a computer program, right? People have some, you write some MATLAB or C programming before, right? You can program this thing easily. Okay? You see that? Okay. And we understand later on, this number, how can we construct those numbers so that it do something useful for us? My cell phone, your cell phone, has something like this. Really have something like this. And by changing those numbers, we can do something very, very interesting. Okay. Okay, so now so these are two key concepts here. Signal and systems. So let me maybe now show more abstract type of systems. More abstract type of systems. I'm going to define now for you a class of systems. A class of systems that are quite general, okay, but it have a quite remarkable property. So I'm going to define here now a definition now of the so-called linear time invariant system. Systems S. So I have a system S, like this black box. But now I'm going to assume that it does specify two properties. One is a linear system, two is a time invariant. So if, okay, let me satisfy two properties. One is a linear, okay, obviously linear time invariant. Linear, namely that if I have, okay, let me denote this form here. So I have this system here, and I can write them y of n is equal to s on x of n. Okay, so I cut this signal, I put the whole system to it, and boom, it gets me this out. Like the example I showed you. So now I have systems here. And when to the linear systems, in the sense of now if I have A1 have x1 n plus A2 x2 n. Okay. I take the output, I take these two signals here, now I take the linear combination of them, and then I put them through the systems. Then the output of that system can be written as really just simply a linear combination of the two output of those two original inputs. Okay, it makes sense? So it's a little bit wordy, but in mathematical terms, simply written as I have an S. Remember, S now is a system. Take not just one number, but give you one signal, give you another signal. So I take that x1 of n plus a2s of x2 of n. Okay, so this is a linear property. A system that satisfies is a linear system. Okay, so that is a satisfied form. Is a L. Okay, this Helmholtz called LTI. The second property you have to satisfy is the time variant. Time variant simply put, I have a signal, right? So here I go through the systems. I have output here. Okay, right? Now I take my input. I delay them by some time. I put through the system. The output simply delayed. Okay, so that is called time variant. So simply put, is I take S of the signal x n minus n naught here. So n naught here is a fixed, okay, it's a fixed number. Then our output here is simply we have trouble here. Let us assume that I have y and n. Okay. Then I take S of x n minus n naught. Then that's simply just give me 1 of n minus n naught. Okay? So that's describe what? If then okay. So a system, let me repeat, a system's S satisfy this two property is called a linear time invariant system. So called LTI. Okay? So let's have a look at that. Now, it turned out that two things. Remarkably, many systems around us can be modeled or can be assumed as an LTI system. Second, they have some very remarkable property which I'm going to talk about now. So you might have a system here, for example. Nobody think about this system. It's very complicated. I have a system here. How can I describe the system to a computer? Right? And you think about how can you describe the systems to a computer? Right? I have to build a systems, right? And I have to instruct the computer to mimic a system to me. How can I describe them to the computer? Any suggestions? Input response, right? Okay, so you're one step ahead of me. But you see the problems here, right? If I have a system, that means just put in the input, I got something out, right? Not a black box. Put something in, something come out. And to describe that, you have to describe all different reaction to all different inputs. Right? You need a transfer function. It's something to describe the system. So it turned out to be a very complicated generally to describe the systems. Right? But very remarkable if I have a system. So I'm going to state a theorem here now. So we have a theorem here. Let me start a theorem. So let S be an LTI system. Okay. I have here an LTI system. And as something that is suggested, the unit pole response, or N here, is equal to the output of that system S based on the signal I used before, the unit pulse response, the impulse. So I take